You hear it all the time, right? The incredible power of big data, how analyzing all our information can cure diseases and make the world a better place. But how do we actually do that without giving up our own personal privacy? So that's the big question. And today, we're going to dive into a really powerful solution called differential privacy.
And really, this is the core paradox of our time. On one side, you've got these massive data sets that can help us do amazing things, cure diseases, build better cities, you name it. But on the other side, every single person in that data has a right to privacy. For the longest time, we thought we had this figured out. But it turns out, that whole idea, it's completely broken.
So for ages, the answer everybody leaned on was anonymization. The thinking was pretty straightforward, just strip out names, addresses, the obvious stuff, and the data would be safe to share. It sounds great, super simple, but it was a deeply flawed idea from the start.
I mean, let's be real. In the world we live in now, where everything's connected, the idea of truly anonymous data is just a myth. The funny thing is, the very details that make the data so valuable for research, that's the exact same stuff that makes it super easy to trace right back to you.
And look, this isn't some academic what-if scenario. These things actually happened. Researchers took supposedly anonymous hospital data and matched it with public voter info. All they needed was a zip code, a birthday, and a sex, and bam, they found the governor of Massachusetts' private medical history. In another crazy case, Netflix put out this huge anonymized data set for a competition. Well, researchers just linked it with public movie ratings on IMDb and started figuring out who specific users were. But here's the kicker. The danger isn't just about someone figuring out which line of data is yours. Even if they can't pin your name on a specific record, they can still learn incredibly sensitive things about you. And it's shockingly easy to do. Let's talk about something called a differencing attack. It is so simple, it's brilliant. So imagine an attacker knows some guy, let's call him Mr. Smith, is in a hospital's database. First, they ask a general question. Hey, database, how many people in here have the sickle cell trait? Let's say the answer is 15. Then they ask a slightly different question. Okay, now how many people besides Mr. Smith have it? If the answer is 14, well, they just learned Mr. Smith's private health info. Just like that. 2 questions that seem totally harmless, and his privacy is gone.
So you see, even those high-level summary stats that seem so safe, nope, not safe at all. Scientists even found that just by looking at aggregated genetic data, the overall frequency of certain markers, they could figure out if a specific person was part of that study. This was so bad, so serious, that the National Institutes of Health actually had to pull the plug and shut down public access to that data. It just proves beyond a doubt that the old way of doing things, just blacking out a few details, is completely, totally broken. Okay, so if the old way is broken, what's the fix? Well, this is where differential privacy enters the picture. And it's not just a patch, it's a complete shift in how we think about this problem.
The first step is just admitting that the old way is a dead end. We can't keep trying to make the data anonymous. It's a game we're always going to lose. The solution has to be something completely different.
And that new way of thinking is built on a better promise. It's not a vague hope. It's a formal, mathematical guarantee that's made to every single person who contributes their data.
And get this, here is that promise. That is an incredibly powerful statement, right? It's basically saying that nothing bad will happen to you because you let your data be used. It doesn't matter what other info an attacker finds, your participation won't be the thing that hurts you. So let's get a little more formal. Here's the definition. And the really key thing to grasp here is that differential privacy isn't about cleaning the data. It's a property of the analysis, the algorithm itself. It's a mathematical guarantee that if you run a study with your data and then you run the exact same study without your data, the final result is going to be pretty much identical. Your data becomes statistically invisible. Okay, so how on earth can you make a promise that strong? I know, it sounds a little bit like magic, but the way it works is actually pretty easy to understand.
The whole thing hangs on one core idea: plausible deniability. Basically, the system is built so that any answer it gives out, well, that same answer could have been produced even if your data wasn't in the database to begin with. So you can always deny you were even there.
Okay, here's an example. Think about a huge medical study on smoking. The main finding, that smoking causes cancer, that's a big picture truth about the population. It's not because of any one person. It doesn't matter if your specific data is in that study or not. The conclusion is going to be the same. Differential privacy just takes that idea and makes sure it holds true for any kind of analysis. Your single data point doesn't sway the result, so the result can't be used to learn anything about you. So, how does it do this? Well, it adds a tiny, carefully measured amount of randomness, what we call statistical noise, to the results of every query. You can think of it like adding a little bit of fuzziness to the final answer. And this noise is calibrated perfectly. It's just enough to hide what any one person contributed, but it's small enough that the big overall patterns in the data are still clear and useful for research. Now, this is an amazing breakthrough for sure, but, and there's always a but, it's not free. It actually forces us to face a really fundamental trade-off that you just can't get around. And this is a really important point. It applies to any privacy system out there. It's called the fundamental law of information recovery. And it's basically saying that if you get overly accurate answers to too many questions, you're going to destroy privacy. And not just a little bit, in a spectacular way. Which brings us to the ultimate balancing act. It's pretty simple, really. The more noise you add, the more privacy you get. But the more noise you add, the less accurate or less useful the results become. You're always trading one for the other. So differential privacy doesn't magically make this trade-off disappear. What it does do, which is so powerful, is give us a solid mathematical way to manage it. It lets us actually measure how much privacy costs for each question we ask. This creates something called a privacy budget, so we can be smart about how we use our data and make that budget last as long as possible. And that really leaves us with the big final question. And this isn't a question just for the tech folks or the mathematicians. This is a question for all of us, for society. Because as we use data for more and more important decisions, we're the ones who have to decide where that line is. What's the right balance? How much accuracy are we really willing to trade for real privacy?